Hello, welcome to Open Logic. In this video, we're going to look at how transistor serves as the fundamental of integrated circuit. This is a symbol of a transistor, specifically MOSFET transistor. In real life, it can be manufactured as a discrete component, but more importantly, it can be fabricated on a silicon wafer at a very small size, where huge numbers of transistors are connected to form an integrated circuit. The functionality of a transistor is that by controlling the input signal here, we can control the electrical signal through this channel. If we plot a graph to map the relationship between the input and the output of a transistor, we will get a line like this. There are two regions of interest in this graph. The first one is this linear region, and the second one is this saturated region. If we apply an input signal within this region, this would be the corresponding output signal behavior. Application-wise, we can create a circuit like this where we apply the input signal here and the output signal would be amplified. This application is more of an analog nature. Now, at this saturated region, the output signal remains relatively constant regardless of the input changes. So, imagine we pick only 2 points as our input. This would be the corresponding output. Application-wise, we have created an electrical switch where by contouring the input, we can turn on and turn off the channel here. This application is more of a digital nature. Now let's focus on the switch behavior. If the input is high, the output would be high, and if the input is low, then the output is low. We can align these two signals in time to visualize their behavior. At this point of time, you may ask, if the output is exactly the same as the input, why not connect the input directly to the output? It's not wrong to think of it this way, but this is not about switching capability. This is about control capability, which we'll look into later. But before we go there, you should know that there is another transistor where its polarity is inversed. The symbol looks similar, but there's an extra circle. If the input is high, then the output is low, and if the input is low, then the output is high. Now, generally, there are two ways to connect the transistors. The first one is to connect them in parallel, and the second one is to connect them in serial. For the ones connected in parallel, enabling either one of them or both of them would allow the electrical signal to pass through. Whereas for the one connected in serial, both transistors must be enabled in order for the electrical signal to pass through. In a very general manner, the parallel connection achieves a simple OR operation, and the serial connection achieves a simple AND operation. Having said that, these two circuitries are not sufficient to form a digital logic gate. Do you know why? Now let's put an output port here to understand what's going on. When we enable the transistors, practically this becomes a short circuit. While this is a live connection, we cannot really tell if the output port is driven by the high voltage here or driven by the ground here. For a digital logic gate, we need to make sure that the output is either driven by the high voltage or the low voltage. Looking at these parallel transistors, if either one of them is driven to 1 or both of them are driven to 1, then the high voltage will drive the output port. Now at the same time, we want to block the ground from driving the output as well. And the way to do this is to introduce an exactly opposite circuitry here. We know that the high voltage is blocked when both transistors are driven to 0. So intuitively, we can use these inverted transistors in series like this. When the two inputs are 0, these two transistors are enabled and the ground can drive the output. In a similar manner, for this circuitry, when both inputs are 1s, we want the high voltage to drive the output. But when any of the input is 0, we want the ground to drive the output. And therefore, we can create a circuitry using inverted transistor connected in parallel like this. Previously, we have looked into how this inverted transistor can invert a signal polarity. But now we know, in order to create a complete digital logic gate, we need another transistor to enable driving from the ground like this. And there we go, these are the three basic logic gates. This is an OR gate, this is an AND gate, and this is a NOT gate. And now to answer an earlier question, by connecting transistors in various manners, we can accomplish functionality beyond the switching capability of a transistor. Mathematically, these three logic gates can be represented by an equation respectively. As I was saying before, on a silicon wafer, we can fabricate a lot of transistors to create an integrated circuit that can perform complex operations. And now here comes the question, how are these three simple logical operations related to complex calculation? In fact, can they even perform simple mathematical operations such as addition? Well, interestingly, they can. First, let's rearrange the equation here and let's add in all the other equations. So far, the equations are in decimal, so first, let's convert them into binary. Now, instead of using the addition operation, let's use a table to map out the relationship between the inputs and the outputs. Intuitively, we should know that the logical operation is performed on a single bit. Since the output has 2 bits, we can further divide the table into 2 different tables, where the first table handles the first bit and the second table handles the second bit. These tables are known as a truth table. We can use them to design digital circuit. For example, we can focus when the output are 1s. In this case, output is 1 when A is 0 and B is 1, and we can represent it by using a circuit like this. And similarly, output is 1 when A is 1 and B is 0, and we can represent it using a circuit like this. And these are the 2 cases when the output becomes 1, and to fulfill the intent of the table, we can combine these 2 circuitry by using an OR gate. If this is new to you and you're having doubt, I'd recommend putting the input values here and go through the circuit point by point to figure out what the output value is. For example, if both A and B are 0, then these points would be 1, 0, and the result of this AND gate is 0. These points would be 0, 1, and the result of this AND gate is 0 as well. Since these 2 points are both 0, the result of the final OR gate is 0. And this fulfills the first entry of this table. You can try out all the other values in the table and you will be able to confirm that this circuitry is indeed representing this truth table. Now, this circuitry is quite common. Its output is 1 only when one of the input is 1. And therefore, a special symbol is created to represent this circuit. And it is known as exclusive OR. Now, if we look at the second table, this is even simpler than before. This is practically the truth table of an AND gate. And to combine it all, an addition operation can be represented by 2 circuitry. The first bit is represented by an exclusive OR gate, and the second bit is represented by an AND gate. And there you go, by using different logic gates, we can construct circuitry that can achieve mathematical operations such as addition. And having said that, these 2 circuits are not full functioning adder because they can only operate on 2 single bit numbers. And since it is incomplete, this circuitry is known as half adder. If we look at the addition operation, for example 15 plus 7, the result is 22. We can actually break down the operation by digit. For example, 5 plus 7 is 12, and that's why the result is 2 and there's a carry of 1 here. And at this point, 1 plus 1 equals to 2 and therefore 2 here. If we look at this from a binary format, the procedure is the same. Other than the 2 numbers that we're trying to add, there is a carryover that we need to consider. And for the first bit, there is no carryover and therefore the carryover is considered 0. What it really means is that the previous truth table is incomplete. To make it complete, there are actually 3 inputs, the 2 numbers A and B and a carry in. Now once again, if this is new to you and this is totally confusing, I'd recommend going through the truth table and use a method called Karnaugh map to come up with the digital circuit. But for this introductory video, I'm gonna use intuition to create a circuit based on what we've already known. Previously, we have known that a single bit addition can be divided into 2 parts, where the first bit is the result and it is achieved by exclusive OR operation, and the second bit is the carry and it is achieved by AND operation. And this would be the circuit to represent the 2 operations. And now to extend it to 3 single bit addition, first let's focus on the result. A plus B plus C in is actually the same as A plus B first, and then the result is to plus with C in. And therefore, if this is the circuit for A plus B, to add the C in, we simply need another exclusive OR gate like this. As for the carry, if you think that you can also cascade it like this, then you are very wrong. The requirement for carry is that if there are two ones in the addition, then there is a carryover of 1. When there are only 2 single bits, AND gate is the simplest solution to achieve this result. But when there are 3 single bits, AND gate is no longer sufficient. And now that we've understood the requirement, we can look at it like this. If A and B are 1s, or if A and C in are 1, or if B and C in are 1, then the result is 1. And therefore, this is the circuitry to represent the carry. By combining these two digital circuits, we now have a full adder. If we simplify this circuitry by using a block like this, where there are 3 inputs A, B and C in, and 2 outputs result R and carry out C out. The addition of 2 single bits can be represented by this block. For the next bit position, we need another full adder and connect the carry out from the first adder to the carry in of the second adder. And for the first adder, the carry in can be tied to 0. Now for the subsequent bits, we just need to cascade the circuitry one by one. And thus we have achieved the addition operation by using logic gates. Now other mathematical operations such as subtraction, multiplication and division can also be achieved by using logic gates. But in order to achieve that, we'll need to understand the various constructs of logic gates, which we'll do in future videos. Alright, thanks for watching. I hope the video has been helpful. Do support by clicking like, share and subscribe.